Yeah, okay, welcome back. So let's keep continue the mechanical property. So the mechanical property is one of the important mechanical property is Young's modulus. So from the Young's modulus can represent the how strong or how strong behavior of solid material. So if they choose a very large Young's modulus, yeah, large value in the Young's modulus, at that time the mechanical shows a very small deformation or large resistivity with respect to the forces. So those kind of things can be result from the some bond behavior, so that you guys will think about so those kind of energy curve with respect to the distance of the two atomic distance. Similarly, so that if they have this is the energy curve, so that you guys can be changed that to the forces divided by the drive the by the distance at the time. This process can be looked like this, and then this slope also can be derived by the distance again. So that means that this can be is a second derivative of the energy curve, maybe. So from there, so that if they show a very large slope, and that means that they show a large resistance. That means that the high Young's modulus. This is Young's modulus, yeah, normally. So that to distinguish the energy, I usually use the Y. This Young's modulus is small, so that in the atomic scale point of view, that we can say that this red material is strongly binded each other, the blue one is weakly binded each other, so weak material. So that's the concepts of the details about the mechanical property. So let's discuss about another elastic property is from the shear stress and strain relationship. We can also define the shear shear modulus, like we say that G. This shear stress behavior, stress strain behavior also follow the Hooke's relationship. So that from here, shear stresses is just proportional to the shear strain with some coefficient G. So that next concept, elastic property is bulk modulus. So in the under the solid is under the some hydrostatic pressure cases. At that time, that this initial volume can be reduced by that pressure. At that time, that we can also define some volume changings and looks like this. We do not define the exactly, but from the initial volume, and then that's the delta V is volume changing due to the high pressure. So that they also follow some linear relationship that coefficient is a bulk modulus. So the bulk modulus can represent some volume changings relationship to some pressure. So that's also important property of the solid material. But those kind of Young's modulus and shear modulus and bulk modulus has some special relationship. But in this chapter, so I cannot derive that relationship simply. It is because that without the mathematical equation about the pulse equilibrium equation. So to understanding that equation, you should learn about the statics first. And then next solid mechanics chapter, maybe the next year, Professor Yang in our department, so they will teach us about those kind of solid mechanics, so that after the running that topic, you guys can easily understand it. But anyway, those kind of shear and bulk modulus is a strongly relationship with the Young's modulus and Poisson ratio. It is because that anyway the solid structure will show the same in linear relationship, and also that in the atomic scale point of view, that their atomic bond distance is affected to those kind of macroscopic behavior anyway. So the depending on the material, so bonding networks, their Young's modulus is will slightly differ. So first is a metal alloy shows a very high strengths. It is because that they are strongly binded to each other. For example, the metal binding or some ionic or covalent bonds. So the ceramic structure shows a highest value. It is because that their system. So the like ceramic structure, so that they have a strong covalent bond. But however, compared to the metal or ceramic structure, polymer has a very weak interaction between the chain. Actually, the polymer itself, has a very high strength, which consists of the covalent bonds. However, that between the polymer chains, they have a very weak van der Waals interaction. Finally, they result in the very weak mechanical strength. But those kind of polymer structure can be enhanced by the adding some fiber structure. We call it those kind of structures composite structure. Composite structure is consists of the two things. First is a polymer matrix, and then the other thing is some very fibers embedded into these polymer matrices. So due to those kind of fiber structures, so the mechanical strength is slightly or extremely highly increased depending on the types of the embedding the material. Let's think about the linear elastic relationship. From some equation, from Hooke's equation, we can derive the when we apply the forces to the solid material, how much the solid will be deformed. So from here, so let's think about the Hooke's relationship, stress and strain relationship. From here, stress is defined by the forces over the cross-section area, maybe the A0 in here. And then Young's modulus is material characteristics, and then strain is defined by the how much changed by the with respect to their initial length strengths. So and then recombining this one to the looks like this, and then A0 and Young's modulus to the below part, and then L go to this direction. So that finally we obtain those kinds of equations. This is L0. So similarly, the lateral displacement delta L is when you apply the Poisson ratio, and looks like this, you guys can easily derive it. And also that we can also calculate how much the angle are rotated by the torsion or momentum forces. So from here, you guys can easily simply where is it? Young's the torsion stresses is proportional to the, and looks like this. Shear stress is just proportional to the shear strain with multiply the shear strain, and then the cross-section area is A0, and then shear forces is how we can define the forces actually, just saying just like this. And then shear modulus, and then rotation angle is L0 over the delta angle is just alpha. So and then the A0 is do you know that cross-section area of these circles is maybe the pi over R0 maybe. And then second one, forces, how can you define that forces? So maybe that from the momentum and forces relationship, and then momentum is force and then cross arms, and looks like this. Maybe am I right or wrong? I'm not sure. That from here that R over M, put this value to here. And then last one is I think that we needed one more 1 over R to here. So the from the here maybe the I say that this changing is just alpha, but I think that I slightly wrong. So that this arc length is slightly, how can you say that alpha zeta? So that maybe that must become the looks like this. So that this R is go to the R. So finally we obtain the R over the R power of the 4. So that those kind of way we can obtain those kind of some relationship. So I think that will learns in the solid mechanics more details, but however I just briefly introduced those kind of mathematical relationship. So let's discuss more about the plastic deformations. We already discussed about some plastic deformation, permanent deformation. So when we applied some simple tension at that time, initially they will experience some elastic deformations. But however, when we exceed some stresses value, at that time they will show some those kind of dislocation behavior or some large deformation. At that time that we say that the solid will is under the plastic deformation. But those kind of plastic deformation is combined by the elastic deformation, so that the slope are slightly decreased and then the linear relationship is broken. And then after the unloading, at the time that they will return slightly, but however they have some permanent strain. At that time that we say that this is a plastic strain. So that you please do not confusing that this total strain is elastic and the plastic strain, but in this pink region that we have only elastic strains. But however in this red region at the time we have elastic and plastic strains combined each other. But after the unloading, at that time that we do not have any in the elastic strain, so that total strain is just equal to the plastic strain. It looks like this. It is because that from the Hooke's relationship, without the stress, means that stress forces is equal to 0. At that time, the elastic strain is always equal to 0. But however, with the forces at that time, we have those kind of elastic strains just proportional to the forces. And then one more, and then the one thing you should remember that in this region, red region, that I say to you that the total strain is just the summation of the elastic strain and the plastic strain. But in this part, the stresses, how can you say that the stress value is just equal to the depth value? But however, can you guess those kind of total stress? So that although I say that total strain is just the simple summation of the elastic and plastic strain, but however, the always total stress is just elastic stresses only, not plastic. Sorry. It is because that plastic strain does not contribute to any stresses increasement. It is because that during this slipping or dislocation propagation at that time that the energy disappeared or stress does not process, the resistance does not increase, so that the only stresses can say that the elastic stresses. And then next important things is yield strengths. Yeah, stress when the when we say that the stresses exceed some specific value, at that time that this solid material will show the plastic deformations. We have some criteria. That criteria we call it the yield strengths. The yield strengths can be easily calculated theoretically, but however, in the experimentally, we say that after the loading and unloading cycle, if they have a permanent strain value, those value 0.2 percentile or 0.002 cases, at that time that stress value is yield strength. If you do sometime, we ideally that value is yield strength. It is because that in this red reason that the solid metal will show the plastic behavior anyway, but however after the unloading in these cases, their plastic strain is very small. It is hard to measure those kind of very small strain, so that to catch it exactly, so that we engineering field they defined those kind of engineering 0.2 percentile engineering actual plastic strain. So at this cases this value is, we say that this is a yield strengths which noticeable plastic deformation have been occurred. So that yield strengths can be tableized in this slide. Metal and some structure will show a very high yield strengths, but the polymer structures can be easily expected very small yield strengths. But you think about that. But there are no yield strengths data in the ceramic structure. Do you guess it? It is because that I say to you that in the previous few months ago, the ceramic structure is consists of the very strong covalent bond. So that means that when we increase these two bond atoms to each other opposite direction, at that time that bond will be broken. The bond strength is very large, but however when you exceed that some stresses value, at that time that crack will be start immediately. But we say that the yield strength is defined by when after the unloading, that if they have a 0.2 percentile value, but however the ceramic or others those kind of structure can be immediately broken, so that they cannot sustain their structure up to the 0.2 percentile. So that means that we cannot measure the 0.2 percentile plastic deformation with the ceramic structure. That's the reason that there are no data in this reason. Similarly, composite structure, we cannot measure the exact yield strengths. Next definition is tensile strength. So tensile strength is maybe that we can say the ultimate stresses which a solid material can sustain their structure. So if they the tensile strength is a maximum stresses on engineering field, so that during the plastic deformation, the solid material will show a very large stresses value. Looks like this. At that time, though, we say that this is a tensile strength, and then they reduced their stresses during the elongations, but finally the solid matter will be broken. Those kind of behavior can be detected in the metal or polymer systems. Maybe the ceramic structure is immediately broken, so that means that it is hard to measure the tensile strengths of the ceramic structure or some composite structures. So due to the reason that the metal and polymer shows those kinds of trend, but the ceramic structure can be anyway, we can detect or measure the maximum stresses. So that due to the reason that the ceramic structure shows those kinds of ranges of the tensile strengths. Yeah, next definition of the material property is ductilinity. Ductilinity means that the plastic tension stress and failure. So that means that the some metal or some ceramic structure will experience some fracture when we apply the too much elongation, and then we defined those kind of thing from the initial strain, and then we check the final lengths, yeah, final strain. So that's the elongation. So that some ceramic structure shows a very small elongation, almost nearly zero. But however, the metal property or some polymer material can be stretched too much, so that they will show a very good ductilinity. That's those kind of concepts. So another ductility measure techniques is defined by the cross-section area. And the next is toughness. Toughness means that like ductilinity, we can check some energy due to the mechanical forces. So from here, when we applied some forces, solid material will show some resistivity stresses value and with respect to the specific strain. The stress and strain multiplication and divided by 1, that become the mechanical work. So that cross-section area can be say that the energy of the solid materials stored in solid materials. But however, after the broken, we can sum the total energies, so that we can say that that's the toughness. If they have a large toughness, means that they can store the energy anyway. But the small toughness shows a small cross-section area. But however, some polymer material will show a very small stresses value, but very large elongation. But the cross-section area, the area is very smaller than this ceramic structure. At that time, that although that polymer ductilinity is very high, but however toughness is low. So that's the slightly different concept. Yeah, next concept is resilience. The resilience is ability of the material to store the energy. So in the previous slide, we discussed about the toughness at that time. But almost reason is plastic deformation. The energy elastic deformation very small. So that anyway, when we increase some solid material, that means that this solid structure has a more higher energy due to some working done by forces. So that this amount part is resilience. So that stored internal energy can be expressed by the stresses and strain, but this strain is infinitesimally small, and then we sum the full ranges. That's the internal strain. So that after the integrated this part, and then we can obtain those kind of relationships. So that's the triangle. So we can also discuss about the elastic strain recovery. So first, in the loading, they will linearly proportional to up to the yield strengths. So that after reach the maximum stresses, some during the plastic deformation, and then when you're unloading that, they are recovered slightly. It is because that the atomic environment, although that they are dramatically changed by the dislocation. However, first near neighbor atoms are similar, so that means that they want to have some equilibrium bond distance, so that they will recover slightly. These slopes are the same when we apply the forces in the loading structure. So we say that this is elastic recovery. After then, we apply forces again. they go to the some yield strengths, but this strengths value is increased compared to the first loading cycle. It is because that this solid structure is already damaged, so that the hard yield strengths can be increased slightly. So that we say that this is a we can also say that this is a hardening, yield hardening. So that when you try to do those kind of loading and unloading cases, so that the elastic ranges is more increased. So that those kind of way, when you synthesized or made, when you make some sword knife, and then many dwarfs hit the knife by the hammer. So it is because that they want to increase the depth yield strengths, those kind of loading and recovering cycle. So that we call it the yield hardening. So that after the unloading, they recover those kind of way, but that material damaged a lot. But however, in these stages, when you apply the again, their yield can be increased more compared to the previous cases. Yeah, next definition is hardness. Yeah, hardness is resistance to the permanently indenting. Indenting means that we applied some particle to the some solid substrate. So large hardness means that they shows a higher resistance to the plastic deformation or cracking. So those kind of things we learned in the elementary school. So that the large hardness is dark diamond. So that diamond shows a very high hardness, but however some very brittle cases, so plastic, some or some aluminum alloy cases shows a very smaller hardness. So that when we are indented by some particle or some very solid things, brittle things, and then when we apply that diamond, there are no permanent deformations. But however, the plastic will experience a large permanent deformation. So from here, so that compared to there are many ways to define the measure the hardness. For first, well known is a Rockwell hardness. So that the major when you use those methods, there are no big damages for the sample. But each cases we apply some specific force. Minor load is 10 kilogram. The major load we can increase slightly, so that those kind of way we can define. So, but there are another hardness is Brinell hardness. Using I'm going to skip the details about how to detect the hardnesses, but there are many ways to those kind of things, so that the details are tabularized on this here. Yeah, next important things is true strain. Until now, we also discuss about the strain, but however, we only discuss about the engineering strain. So engineering, what is the big difference between the true strain and engineering strains? Means that how can we define the stresses? Yeah, we should know that some cross section area first, and then we applied some forces, and the stresses is just defined by those kind of forces and cross section relationship. But the one thing problem, when we apply this solid material experiences pulling out, and then this cross section area decreased due to the Poisson effect. So that real stresses is defined by the real cross section area. This cross section area is smaller than initial cross section area. The true stresses is slightly increased due to those kind of things. So when we consider those kind of area changes, at that time we say that this is a true stresses. And then true strain is slightly differs, looks like this. And then true stresses and true strain has those kind of relationship. So to derive those kind of relationship, I think we need some slide. Sorry, where is the slide? Oh, okay, here. So yeah, I say too that true stresses is just a relationship between the forces, applied forces, and real cross-section area. From here, yeah, we should discuss about some volume change without discuss about volume changing or volume conservations. Yeah, how can we define the volume? Yeah, first cross-section area and their lengths. This lengths is those kind of thing. Cross-section area L is this L, so that the volume. But this is equal to the initial cross-section area and initial strains, and looks like this. Yeah, from this relationship we can convert it. Looks like this: L0 and over the L and pulses, and then A0 and L0 and LF. But this definition is our first engineering stresses definition. From looks like this, and then L0 and L, and then this part can be changing the and looks like this. It is because that the epsilon E is just expression is looks like this. So those kind of way, how can we maybe that two things here, maybe the engineering stresses and expression and looks like this. This is engineering stresses, so to here, and then the engineering strain can be expressed and looks like this: 1 over L minus 1. So you can put here. And the next is true strain. True strain is just increment from our current lengths, and then how much increased this DL from L0 to the L. Our initial length is L0, so that from here the obtained and looks like this, and then we can also change using that relationship. So those kind of way we can define the true strain and true strain and engineering strain relationship. Yeah, okay, let's go back to the slide again. So next is hardness. Yeah, I say to you that those kind of relationships. So when we applying loading and unloading cycle, their yield strength is slightly increased. Those kind of processes is hardening processes. If they have some those kind of big changes at that time, they say that the large hardening, but there are no deformation at the time. The solid material experience perfect plastic deformation, and at that time there are no small hardening. So at that time we don't need to think about the hardening for the solid material. But those kind of to fit those kind of relationship. So this is a true some value, so that maybe that those kind of hardening can be expressed by some mathematical relationship with K is some proportional coefficient in the N is power value. So but however those kind of fitted value can be determined by some empirical fitted value, so that actually yeah, let's discuss about more detail. So that the stresses is just expressed by the some strain, but we already have some value to here. But in this region that is a Young's modulus. However, to discuss about those kind of region also more, so that value is slightly changed to K and looks like this. But to fit that slope, we apply the very some power hardening value. If we have some small value at the time, that we can express the small still. But however, if we use the very large value, the strain effect is dramatically decreased. At the time, we say that that value is equal to the kappa. But anyway, so that to fit that value, we just use that empirical value anyway. Yeah, so there are many concepts about to measure the material property. However, when we measure the material property, there are some human error. So to reduce those kind of statistical error, we should know that the concepts of the mean and standard deviations. But however, this is very simple cases. But the one thing more important thing is the safety factor. So when we design some solid structure, we do not know that the exact applying forces that solid material. But for the safety, we should design the very safety structure with good material. But however, to be sure that those kind of safety, we use some safety factors. Yeah, some solid material has some specific yield strengths. But however, if the stresses does not exceed this yield strengths at that time, we don't need to worry about it. But however, we are not sure that how much forces will be applied to this solid material. So at that time, that we should put some the proper margin, so that this n is slightly larger than 1. That means that the allowable stresses is and looks like this, and then but when we put some of this n to looks like this, and then allowable stress is just half compared to the yield strengths. So that if we need to the very safety at that time, we can increase these safety factors anyway. So if we need the safety factor 5, and then their diameters and their yield strengths looks like this. The yield strength is 310 megapascal. They are extremely 10 cases and looks like this. But how much sizes we need to not exceed the yield strengths or with safety factor 5, and then we can easily calculate those kind of relationship. We have a yield strengths value and the safety factor 5, and then the applied loading is the 220,000 newtons, and then cross-section area is pi r square. So we do not know that diameter yet. So anyway, but the remains value is already determined. So that finally the diameter is 0.067 meter, 6.7 centimeter. So those kind of way we can use the at least 6.7 centimeter diameter the load. This is a summary. So in this chapter, we learned about the stress and strain concepts, and then to explain the mechanical behavior, we learned about the plastic and elastic behavior, and also we also several mechanical definition: toughness, ductility, hardness. So that I think that's the very important concept for to understand the mechanical characteristics. So that please, if you have any question, please contact me anytime you want. Thank you.